Good afternoon, everyone. Today, I will be talking about the principle of least privilege in cloud authorization. Let's start with a brief introduction to cloud authorization. Suppose Alice is asking Zoom to create a calendar event for her. Zoom will then go ahead and talk with Google Calendar, say, give me a token to access Alice's calendar. Google Calendar will need to confirm with Alice whether she allows Zoom to access her calendar event. Here, we see a user is trying to grant a third-party application limited access to an HTTP service without revealing the user's credentials. This is exactly what cloud authorization protocols like OAuth are designed for. Here, the limited access is also referred as OAuth scope, which is the set of permissions requested by the third-party app. Coming back to our example, on a web page that Google Calendar shows to Alice, there's a line saying, view and edit event on all your calendars. This is the OAuth scopes we were talking about. Now, suppose Alice clicks continue. Google Calendar will then issue a token to Zoom. Later, Zoom can use this token to access Alice's calendar event. So in these simple examples, we see three entities interacting with each other: user Alice, client app like Zoom, which is requesting access, and an API server like Google Calendar, which hosts HTTP service. So what's the problem with this setup? We notice that the above setup relies on barrier tokens, which give access to any token barrier. This means tokens are vulnerable to abuse when leaked or stolen. In fact, token leakage and abuse happens in real life. For example, GitHub has reported stolen OAuth tokens are used to access users' private repo. Similar token leakage or theft has been reported with Hugging Face and Facebook API as well. So in all the above examples, we see there is a vulnerability windows when the tokens are under the attacker's control. Even worse, tokens used in cloud authorizations are fundamentally overprivileged. Recall our example of Zoom and Google Calendar. The scope of the token Zoom requests is to view and edit all the calendar events. However, the privilege that Zoom actually needs is just to create new events and view and edit events it has created. So here we see the tokens are given more permissions than what they need. So our question is, would it be nice to tailor the scope of the token right to the privilege that apps like Zoom actually needs? This comes to the key question we have in our paper: how to minimize the token's privilege while retaining functionality. To answer it, we start with identifying the cause of overprivilege. The first cause we identified is server-defined permissions. In the current OAuth, an API server will need to provide a list of scope it supports, and the client app will need to select those scopes that best suit to their needs. As a client app, it tries to find the best match, even though it is not a perfect match. As an API server, it just cannot anticipate every possible way a client uses their API. Let's take the example of Travis CI. Travis CI developers report in the document saying that they need to request both read and write access to users' private and public repo, just because GitHub does not provide fine-grained permissions that suit their needs. The second cause we identified is statelessness. Think about how we can enforce that Zoom can only create new events and view and edit events it has created. We will need information of which events are created by Zoom. So ideally, we will need a table that records all the event IDs and operations performed by Zoom on each of them. If we found an insert in the table, it means that the event is created by Zoom. This table stands for what we call state information, which is the operations that the client app has taken. However, such state does not exist in the current stateless machinery like OAuth. so enforcing such a policy is not possible. So in this work, we focus on the fundamental overprivilege of tokens used in cloud authorization, and we contribute a least privilege authorization model. Specifically, this model enables the client app to express the minimum privilege it needs and also enable the API server to enforce the minimum privilege requested by the client app. In this model, we also introduce two important abstractions. The first one is client-defined permissions with WebAssembly, and second is statefulness, which enables a new class of least privilege authorization policies. Before diving into the design details, let's take a look at our threat model. So we assume that the client app developer and API server are trusted. This is the same assumptions of any permission-based protocols like OAuth. An important nuance here is, even though we trust the client app developer, the client app itself is vulnerable to security problems that can result in bearer tokens being stolen or leaked. It can happen through phishing attacks, infrastructure misconfigurations, and so on. So our security goal is to limit the abuse during the vulnerability window. The core insight we have in our design is that client app developer always knows the app's minimum privilege requirements. Based on that, we enable client-defined permissions. As we have motivated previously, we introduce state, which is the log of operation the client app has executed on the server. So now, besides the current request information, there's also state information that help us to make authorization decision. We formalize it as an attenuation policy that further limits the scope of the tokens, which will output either true or false to indicate whether the request will be allowed. Also, if the request is executed successfully, we will need to update the state to incorporate information of the current request, which we formalize as a function called fUpdate. This is a state updater that defines and updates state. However, writing this fPolicy and fUpdate is a challenging task, which requires good knowledge of the minimum privilege requirement of those client apps. So, in our client-defined permissions, we enable the client app developers to write those two programs and supply them in WebAssembly. We choose WebAssembly here because we needed high flexibility, portability, and in-process sandboxing, which will protect the server from executing the client-supplied code. Now, let's go through our stateful authorization model in a high level. At the beginning, the client app developer needs to register on the authorization server by supplying 3 pieces of information: the server-defined scope, and the client-defined attenuation policy, and state updater. Then, the authorization server will issue a token back to the client app. With this token, the client app can make requests to the server by supplying the API endpoints, the request and state information, and the token. On the server side, it needs to perform several checks before executing the request. First, it will need to validate the token and confirm that the API endpoint is within the server-defined scope. And then, it will need to validate the client-supply state. After that, it will execute the policy, and only if all the checks are passed, it will execute the actual resource API and finally update state and send new state back to the client app along with the response. Next, let me introduce 3 classes of stateful policies enabled by our work, and we will see how statefulness helps to reduce the token's privilege without affecting the app's functionality. The first type of class is access-only created, which we have seen with the example of Zoom and Google Calendar. The second type is read at most once. Think about a trip planner app built with custom GPT, can easily read users' emails and generate travel itinerary based on hotel and flight booking. By enforcing the reading at most once policies, we can prevent attackers from reading past read emails. Similarly, write at most once is another useful type of policy. Think about continuous integration platforms like Travis CI, which execute users' check runs for GitHub commits. By enforcing the writing at most once policies, we can prevent attackers from tampering the result of those check runs. We also want to note here that our framework provides great flexibility and extensibility to the client app developer. They're free to combine any stateful or stateless policies to define their own attenuation policy and state updater. At the end of the talk, I want to share some evaluation results in our paper. We compare the end-to-end latency when using the vanilla OAuth and our stateful authorization framework, stateful auth for short. Our goal is to analyze the end-to-end latency in relation to the quantity of objects per request. So we set x-axis as the number of objects per request and y-axis as the end-to-end latency. We observe that when only executing a single object within the request, stateful auth introduced 4.3% increase to the end-to-end latency compared with vanilla OAuth. When the number of objects increase within a request, both the network latency and the server-side latency increases due to the extra data that transmitted and the sequential processing for each object on the server side. So to summarize, in this work, we focus on the fundamental overprivilege of tokens using cloud authorization due to server-defined permissions and statelessness. To tackle it, we contribute a stateful less privilege authorization framework that enables the client app to express its minimum privilege and enables the API server to enforce the minimum privilege with state information. Thank you for listening, and I'm happy to take any questions.